Okay, so the next talk is by Damian Ortiz Rodriguez and Ricardo Noguera.
Well, right now only me. But
All right, only you?
only Damian Ortiz Rodriguez. There
Okay.
are other two co-authors, but they are not here.
Okay, so we'll forget them.
Yes.
The dominion of gene interactions, a self-organized level of complexity, and an instance of higher order patterns.
It's a bit changed. Universal patterns, higher order patterns. In general, you will see it's the same issue. Well, what I want to talk about is, first of all, what is gene interaction, then how gene regulatory networks and like interact, forming something that I'm calling the dominion of gene interactions, and I'm explaining what is that. Then interaction rules and dynamics of the networks, and then how this relates to the idea of morphospace, and then also the relationship with natural selection, and how I think all of that is kind of a universal tendency. So the objectives were like to show how gene interactions assembly in macro networks and that underlie every characteristic, and how they restrict the possible phenotypic variation that can appear in nature, and also, well, how they and natural selection can be seen as different instances of the same thing. So for example, a common definition that if you ask a molecular biologist or an experimental geneticist that you will get of gene interaction is a phenomenon that occurs when two mutations in the genes produce a phenotype that is surprising on the lack of the individual mutations, sorry. And this is very similar to, well, the concept of epistasis, which has also been defined as the deviation from the linear model of a gene contribution to a quantitative trait. So in general, these are all phenotypic perceptions, but all of them are underlied by functional gene interaction, so the influence of the biological effects of a gene by others, like physical thing. So the phenotype of organisms, as you can agree, is not... Do I have some kind of pointer?
No.
Oh, well, I will do with something. Yeah, never mind. So it results from... but I mean, right now I can follow. The complex interaction between many genes and environmental factors. And it can be understood as the interactions like between gene products that form like developmental pathways and signal transduction pathways, and also the biosynthesis pathways, which include the metabolic networks. And you can also see it as the regulation of gene expression, which can be seen as a co-transduction process from like a storage phase of a living being to the morphofunctional one. So in this process that includes transcription, addition, and translation, you get a lot of processes, and they only act in this part physically. But so interactions can be grouped in gene regulatory networks, and this is mostly said in context of the regulation of gene expression. But the different kinds of networks can be seen as functionally interconnected, like all the metabolic processes then influence what can happen, like all the source of material for other regulation. So everything is interconnected. And so the interconnection of all these networks make up cellular and organismal macro networks. And this is what I'm calling the dominion of gene interactions, which also has been called interactome, but is not just the collection of interactions. It also allows for the participation of stochasticity and environmental processes. So it's a level of complexity on its own. And now, gene regulatory network models, that probably many of you do or all of you know, can explain like specific parts of this micro network. And in these models, you know that the nodes are the genes and the connections are the interactions. And in this specific one, which is from feral morphogenesis, there is this configuration in which only the genes that are signaled in gray are on, and the others are inactive, off, and this gives you petals. And in other configurations, other set of genes on and others off, you get carpels, stamens, and tepals, and sepals. So this is actually a real world model. I mean, the logical rules were derived from experiments, from nature, and so every model has certain topology and certain rules. And well, this is a toy example model based on this one. And in this one, there's 4 genes, with 2 connections each. So the configurations in which this network can be are 16. These are all of them. So off, and yeah, so on. And they have certain rules by which the genes influence each other, they interact. So in this case, when this and this are off, this one will also be off. And when a gene receives different signals, different inputs, it will be then on. It will become active. So you can see by these rules, you can build up this, which tells you kind of the immediate fate of the network. And by this, you can build the system dynamics, which in this case is represented by this diagram that also resembles a network. And so if at the start you have this gene on, the system dynamics tells you that it will tend to go to this other state with this other collection of genes on, and eventually it will be in this other state in which all the genes are off. And if you do this for each of the states, each of the configurations of the network, all of them will converge to this point, which is the attractor. And the attractor, as I told you in this previous one, in this case, it is a phenotype. So actually, you can modify the rules, and the alterations to these rules can originate new attractors. I mean, this is very simple and is a Boolean discrete model. There are, of course, continuous models with differential equations, but this is in principle how they work. I mean, so you get new attractors and only by modifying this simple rule, which can be achieved by mutation, and you get this new configuration. So they are new phenotypes. But the network can also be obvious to change. So if you change the rules, it can also give rise to the same outcome. So you stay with the same attractor. Then, well, phenotypic variation in nature is then constrained by the interaction rules of these gene regulatory networks. And this takes to the idea of morphospace. Because basically Raup in 1966 in his model that is very well known of the shells of mollusks and brachiopods. He had a set of parameters that he combined to create a plethora of different kinds of shells. And this morphospace is all the possible shells, and only the colored zones are the ones that exist. And yeah, this is similar then to this state space of every dynamic system has a state space, and in this case is the space of configurations, the possible configurations. And the result of the system dynamics is that they tend towards certain attractors. And so you can see that it's like a possibility space. And the occupizations of the morphospace could be the attractors of the dynamic system of these regulatory networks. So you see that only stable forms can manifest in nature. And well, natural selection can act only on the subset of possibilities that these gene regulatory network rules and dynamics allow. And on the other side, well, natural selection allows, as you know, only the survival of the fittest. And the rules is that, well, the differential fitness given phenotypic variation and, like this. Yeah. And environmental conditions, well, that's how natural selection works. It follows the same filtering pattern as the gene regulatory network dynamics, but it has its own set of rules and participating agents. So it's a different dynamic system, and we can think of it as having its own state space or morphospace. What I forgot to say here is that this model has been criticized as being too simple, but you can make it like multi-dimensional. You can add many other variables, but what is important is the idea of all the possible things that could exist and all these searches can happen. So the occupied sections of the morphospace of natural selection could be the proportions and kinds of living beings at a given time. Of course, that's a very simplistic, way of saying it, but it could be a complex thing to do, but it's a tendency. So Alfred Lotka already talked about the persistence of stable forms, because he called like that.
You have 5 minutes.
Oh, okay, I'm fine. Okay. So he called like that natural selection itself. He said like it was like a synonym for natural selection acting beyond the realm of living beings. And he considered it to be a physical principle. But what we're proposing is that, well, natural selection rules only apply in certain contexts. So it's only a specific instance of a more universal pattern, the principle of conservation of stable forms. And the gene-regulated group dynamics would be another manifestation of that tendency. So also, if you talk about clade selection and all these other levels that have been talked about in macroevolution, they could explain as different manifestations of this same principle with their own ingredients and constraints. And actually, you can see this happens in other levels. I mean, you have the chirality issue, where only you have a certain stereochemical configuration of amino acids, for example. You have only certain allotropic forms of the elements. And you, of course, have the self-organized patterns of, well, collectivities, like in this flock of starlings, which make this terror wave and they are attacked without any kind of, central command. So you have also these specific forms of others that they could do. And, well, you can even extend maybe this issue to things like the large-scale structure of the universe, that if you modify certain patterns, instead of getting this, which is ours, you could get another configuration. And of course, and there's also the asymmetric decay of matter. Yeah, that you have a lot more matter than antimatter. And yeah, maybe you think it's extrapolating a lot, but well, it seems to have a certain pattern. And of course, the neural networks, they have their own rules. So you can also see that natural selection follows the same tendency as self-organized patterns, but self-organized patterns and many other things cannot be attributed to the rules of natural selection. So in conclusion, well, gene interactions underlie every function of living beings. They are not exception but the rule. And gene interactions are organized in networks of different kinds, and they are all interconnected in macro networks. Then the gene regulatory networks are dynamic systems, and they have rules, usually in dynamics, which constrain what can appear in nature. So they are a source and a filter of the phenotypic variation, and they are hierarchically previous. So they constrain what natural selection can act upon. And well, they are, as I propose, different instances of the same pattern found across levels of complexity of the universe. Conservation of stable forms, or if you don't think they are stable, of certain forms. But that's the proposal. And well, I thank these people, co-authors and supervisors, and all of you for your attention. Thank you very much.